Dear Professor Holzman and Dr. Sherburne, we are Team 96As with Brian, Shrang, Further, and me, Yoren. And today we are going to give a presentation about our capstone project, which is to build a powder delivery system for laser-based additive manufacturing. Our project, to be concise, is to build a powder delivery system for a 3D metal printer. The whole printing system is mainly composed of two parts, the laser system on the top and the powder delivery system on the bottom. And we are focusing on the designing and manufacturing of the powder delivery system. The challenge we have identified in the realm of 3D metal printing is that its application is predominantly limited to industrial settings, but not commercial usage. Also, existing 3D metal printers on the market can be complicated, as they often lack standardizations in their parts and assembly. Furthermore, the cost of these huge machines, which can range from $100,000 to $500,000, creates a significant barrier for individuals and small businesses seeking to make use of this groundbreaking technology. In response to these challenges, our capstone project aims to develop a 3D metal printer that is more accessible, simple, and affordable. By simplifying the design, incorporating standardized parts, and optimizing the manufacturing process, we hope to reduce the cost of the machine substantially, making it a viable option for a wider audience. Our vision is to spread the 3D metal printing technology and enable individuals, small businesses, and educational institutions to harness its potential for innovation and creativity. Moreover, our design emphasizes portability, ensuring that the users can easily integrate the printer into their workspaces. By achieving these goals, we aim to foster a new area of manufacturing, where the power of 3D metal printing is within the reach of everyone. Next, I'll discuss some of the approaches that have been used by others on the market. First, the laser system can be mainly divided into two types. The left one is the optical diagram for the laser beam powder bed fusion system. It uses optical method to direct the laser onto the powder and to fuse the metal. And the right one is the electron beam powder bed fusion system. It uses electron beams to fuse this metal. Since we won't be working on the laser system, but rather the powder delivery system, these are just some background knowledge for better design on our part. Then let's move to the powder delivery system. Most powder delivery systems are composed of one building cylinders as the part bed and two powder supply chambers as the sources. Also, it needs to contain some power supply and transmission systems, such as the rack and pinion system in the picture, to move the three parts up and down. The working process is also very simple, as the right figure shows. First, the left piston goes up to provide the metal powder, and the other two goes down to accept the powder. Then a roller will spread the powder to fill the middle piston, and the rest of the powder will go to the right one for later use. As soon as the middle one is filled, the laser comes in to fuse the metal. Later, the right one supplies the powder and the roller goes back again. This simple process goes on and on again to produce the metal product layer by layer in the middle piston. For the next part, we will introduce our design based on the literature we have reviewed.
Great. Hi, I'm Shuang Shao, and let me introduce our project design. Here is an overview of our prototype. So what is distinctive about it? First, it is very small in size. To make it portable, it is designed to be only about 320 millimeters in length, 120 millimeter in width, and 160 millimeter in height. Also, to minimize its weight, we used a lot of aluminum metal sheet design in the prototype, including the overall structure and all kinds of other supports. It makes our device as light as at just about 20 kilograms to be portable and convenient to use. And for the platforms, it should be able to move in a vertical direction, So the choice of the transmission system was a difficult question. We at first came up with several ideas, including hydraulic driving, crank driving, and lead and screw driving. After careful consideration, comparison, and discussion, we figured out that the hydraulic system was too expensive to be applied to our products, since we were not expecting a really high price of it. For the crank driving, although it is cheaper, its motion relationship was nonlinear and thus hard to control, while we want very accurate controlling of the platform. So the best choice was determined to be the lead and screw transmission. However, another problem came about. We have to keep the platform inside the tube to make it more vertically, but it should not rotate together with the screw of the step motor. To solve this problem, we tried many different designs and finally worked out a very delicate one. That was to add a step on the edge of the platform to match it with the slots cut on the tube. This very small step could keep the platform anchored at a fixed horizontal orientation, and when the step motor is on, it could go only vertically instead of rotating together with the screw. Moreover, the transmission system that drives the slider of the sweeper was also a tough task. It required a linear motion output from a rotational motion input. However, after calculation, we found that the largest torque of a motor available with appropriate size was not large enough to drive the sweeper directly, which means that a speed-down system was required. The most commonly used transmission system were gear transmission and belt transmission. After consideration, as well as some research and calculation, we figured out that the belt transmission system was the most suitable one. First of all, the belt transmission system has a very little metal-to-metal contact, making the whole system isolated to electric and safe for daily and industrial use. This is very significant advantage over the gear transmission with regard to engineering ethics. Moreover, the belt transmission produces less noise than most of other types of transmission system, which makes it more convenient to use. Last but not least, the belt transmission system is most suitable for the working environment where the central of the input and output axis are relatively far away from each other, which is extremely suitable for our device.
你开始了吗？ I will talk about some detailed design in our powder delivery system. For the powder delivery system, we need two similar subsystems, one for lifting the powders up to provide the powder for each layer, another for layers to forming each layer. To simplify the structure and make it a smaller size, we choose step motors to control the platform's height. The maximum powder size is a 60 mm diameter and 30 mm height cylinder, which is a 85 centimeters cubic. That is over half kilogram. The motor is from McMaster, a popular website to sell the mechanical and control parts. The step motor has a very high accuracy for each step and has a large load capacity to overcome large friction and the weight of the structure and powder. Next is the sweeper motor selection. The sweeper is used to sweep the powder for each layer from the providing cylinder to the forming platform. Its motor speed is 2,485 revolutions per minute and has a load capacity of 6 pounds. Also, it has a size of 2.5 inches multiplied by 1.7 inches multiplied by 1.7 inches, which suits our space allocation well. It has an output transmission ratio of 0.354, which brings a very big pulley turning speed and can make the sweeper move very fast for one go and return. It can make our manufacturing period pretty faster. For the belt transmission system, we use 2 stages of transmission to fix the speed and space need. The first stage belt uses a 17-teeth 2 mm pitch pinion, which links directly to the motor, and a 48-teeth 2 mm pitch pulley. The second stage are 2 same pulleys, which is 36-teeth 3 mm pitch pulley, They are all well tuned to have a good tensor and a common teeth belt. Also, we have some special details. We designed some slot-shaped holes on the structure use sheet metal to have the possibility to adjust the position of the sheet metal, because there may exist some manufacturing tolerance and assembly tolerance. Also, we use lots of rivets to convenience our assembly, making our design more clean, tidy, and lighter. For the cylinder, we use welding methods to fix the place and enhance its strength. On the connection between pulleys and shafts, we also use adhesive method. The last thing is about the motor controller. We choose one which fits our step motor pretty well. Its voltage is 12 to 48 DC and has a number of steps resolution setting of 25,501. Its maximum step frequency is 2 million Hertz, which can control the steps very accurate. Also, the size is 2.9 inches multiplied by 3.9 inches multiplied by 0.9 inches, as can be seen in the picture. It suits our device pretty good. As can be 结束了，没了。
Okay, so now I'm Ryan Agahi, and I'll be talking about our product's place in the market, our current progress, and our future plans for building an affordable powder delivery system for laser-based additive manufacturing. So what is our product's place in the market? What we believe that we've been working on for the last year is something that's geared towards the individual, such as a student or a researcher. And why is that? Well, this is going to be a small and cheap device that's relatively easy to manufacture. So basically an engineer or a researcher can have like a desktop appliance to be used for small scale rapid prototyping. And it can be used for a wide variety of industries, basically anything you can think of, whether it be automotive, space, biomedical, etc. And researchers can use our product to create prototypes and parts very easily, quickly, and inexpensively, allowing them to do their designs and kind of work in practice to make sure that they can make all the necessary adjustments needed before committing to a larger scale product. And right now, if you're trying to do these designs and have it manufactured, you're going to have to outsource the work to a different company, which creates a lot of lead time issues and a lot of cost issues as well. As you can see, if you want to have one of these systems, they're super expensive, around $100,000 to $500,000. So being able to put this technology in the hands of the individual for a lower price is something that would help like researchers around the world basically just make parts and do rapid prototyping a lot more quickly, easily, and cheaply. And so our current progress. So basically we placed our order over a month ago, and it was slightly delayed and also a little incomplete. So when we got our order, we realized that we needed a couple more raw materials in order to fulfill our project and manufacture all the parts needed to build our powder delivery system. One of the issues is we didn't have access to URSO, which is the Berkeley website that you order parts from. And the individual responsible for ordering our parts had some delays in the process, which further delayed our timeline. We learned that, people that are on the exterior of our project might not be as invested as we are. So that's something we're going to take into account for our future projects. And but we got everything we needed, and we're finally moving forward with the manufacturing process. And so we're really happy about that and excited to see our vision come to life. We aim to finish our prototype in the next 1 to 2 weeks. And I'll basically describe why it's going to take 1 to 2 weeks now. So we're working with the machine shop closely to get all the parts needed for our system machined. And we had one issue was the aluminum sheets we bought from McMaster. We bought 6061 aluminum, and then we quickly learned from the machine shop that in order to, as you could see from the diagram, have a bend of 90 degrees, we would have to change our design completely, as 6061 aluminum does not bend. It will not bend like that. It'll break. So we'd have to make it like 3/8 of a radius more out, which is something we did not want to do. So I bought material from Ace Hardware and was able to do a trade with the machine shop. So we were able to get the 5052 aluminum needed in order to fulfill the requirements of our design. So basically, I have personally dropped off all the materials to the machine shop, showed them our designs, and basically sent them shop drawings, STL files from SolidWorks, DXFs for parts like this that can be water jetted, and PDFs of all the drawings needed, such as the one you see next to us. So right now, we're just waiting on the machine shop to manufacture our parts and seeing if they have any updates for us for lead times, if there's going to be any costs, and just any additional information from them. Right now, the shop is really, really busy, but we're in close contact with Scott, Dennis, and Alex to make sure that we get this done in the next 1 to 2 weeks. And once we do get our parts machined, our future plans is that we're going to put it all together. And so in the next 2 weeks, we plan to have everything machined, as I just said. And we believe that once everything is machined, it's going to be fairly easy to put everything together. We can probably do it in the same day once we have everything done. So just working with Dennis, Alex, and Scott in the Etcheverry machine shop and making sure everything gets done. And once we have it done, we can put everything together and, test our design. So we're really excited about that. We really appreciate all the help and all the advising you've given us over this past semester. We couldn't imagine doing it with anyone else. And we really look forward to updating you with our finished project in the next 2 weeks. So thank you again, and hope you have an incredible rest of your day.